Is material balance analysis different for reactive system? Today we will answer the question and using this example. If you do A balance, you will notice what comes is 200 and what leaves is 100. Is this supporting what we were saying before, that N equals to out? Clearly not. B balance, you will notice what comes from B is 30 and what leaves is 130 kilogram per minute. All the units are kilogram per minute. So if you do A balance and B balance around the reactor, then things will change. It will not be the same as before, because we have for reactive system generation and consumption. All the other here, if you notice, separator physical, mixing point physical. Consider the reactive system. If you do material balance around it, A balance, what comes from A is 200. What leaves minus output, if you remember the rule, input minus output, so which means minus 100. And then we have plus generation and consumption. There is no generation of A. A is being consumed, is being lost. We have 200, and if it leaves, we have 100. So there is decrease flow. So we will say plus 0, we don't have any generation. And then minus the consumption. What will be the consumption? We don't know. This is what we want to find. To explain why 200 is not equal to 100. Why we have this terrible math mistake. Then it will be equal to the accumulation, and if it is steady state, as we said, it will be 0. Now find the consumption. If you have minus consumption, then the answer you'd expect it to be positive. 100, move the consumption to the other side, to the 0 side, it will be 100, the consumption. And now check the equation. Is it correct or not? Is it logical or not? Is it a valid equation as we said before or not? We'll say 200 minus 100 plus 0 minus the consumption. 0 should be equal to 0, and this is the case. The difference in this number, 200 equals to 100, is not true because we forgot the consumption term that we needed to add. Similarly for B, material balance, what comes from B is 30 minus what leaves from B, which is 130. You will see that B increased, so there is a generation term we need to add, which will be the thing that we want to find to explain why we have this terrible math mistake. Minus consumption. Do we have consumption of B? We are gaining B, so we have no consumption. And it will equal to, if it is steady state, it will be 0. Now find the generation, and you would expect that it will be positive because it's generation after all. Both these two numbers to the other side, you will say generation will equal to 130 minus 30, which will be equal to 100. Now checking if it is a valid equation or not. 30 minus 130, which is the output, plus generation we found 100, minus 0 consumption. This should be equal to 0, so that we have a valid equation 0 equals to 0, which we have. Here is the interesting thing about mass. If you do overall balance on the reactor, what comes overall is 200 plus 30, and what leaves overall will be 100 plus 130. Are they the same? Yes, they are the same. 230 equals to 230. Proving that the total mass is conserved. The total mass cannot be generated, the total mass cannot be consumed, but the component masses can be generated and can be consumed. That's the biggest difference I needed to emphasize on. Another thing to notice here, my friend, is the fact that A did not completely go away. We still have some amount or flow left the reactor. This is actually the situation you will face a lot in every reactor. It's very, very hard to completely make this 0 when it is leaving. And this is actually one of the biggest reasons of having a separation process. We only want B, we don't want A. A is a trouble for us. We want to get rid of A so that we can have only B. If there is some flow of A that will leave, then it means we have a percentage. We want to find this percentage, that if we multiplied it by the flow that will come to the reactor, we will have the thing that will leave the reactor of the same species, which is in this case A. We call this fractional conversion. Fractional came from the fact that it will never be greater than 1, it will be always greater than 0, and it's very hard to achieve 100% fractional conversion. That is, it's very hard to completely make this 200 be 0 at the end when it is leaving the reactor. Fractional conversion of A, if you want to find it, we call it F. In other courses you will see it is X. In chemical reaction engineering will equal to the flow that was fed to the reactor, which is in this case 200, minus the flow that left, which is 100, divided by what was entering the reactor, which is again 200. And the answer, you will see that it is 0.5, or in other words, 50%, which means 50% of the 200 left the reactor. You see, it is very important. Using the conversion will actually be a key solution to the material balance problem, as we will see later on. Okay, spoiler alert, if you use this conversion, you can find B 30 that enters from the reactor of B plus 200 multiplied by the conversion, which will be 0.5. And you will see that it will be equal to 130 kilogram per minute of B, the same as what is leaving. This is just to make you understand why we need conversion or fractional conversion. We will see later on how to derive or how to find this equation. What we found here is what we call single pass conversion. I'm talking about what comes and leaves from the reactor. But when we talk about overall fractional conversion, I'm talking about what comes and leaves overall process. The recycle at the inlet stream of the A and what leaves the process, which is only the separator from the top. Overall feed of A, 110 plus 90 minus what leaves, and then divided by the feed of the process. Definitely, if you are designing a chemical plant in a true manner, in a true way, not in a disastrous way, then you should get fractional conversion of the overall higher than this 50%, which is the fractional conversion of the single pass type. 95% conversion overall. We learned that we have generation and we have consumption. For a reactive system, we learned what we call fractional conversion, which can be single pass and overall type. Generally speaking, when do we consider fractional conversion? When we have only one reaction. What is a reaction? I know you know reaction and I know reaction, but I want to start from zero with the word reaction, explaining every term in English, because we know the words in Arabic only when we talk about reaction, or when we talk about anything that we are taking right now. The reaction has three things. It has reactants, it has products, and it has what we call stoichiometric equation. I'm sure you know it in Arabic. This is what we call تفاعلات, I think. And this is نواتج. And this is stoichiometric equation, المعادلة الكيميائية. We don't want to know the meaning in Arabic. We only consider English now. Suppose you have this famous example. The stoichiometric equation will not be found in the beginning unless if we do what we call chemical balance. You can check here. We have two hydrogen. We have two oxygen, but here we have only one oxygen. So we need to balance the chemical equation to find the stoichiometric equation. This will be done if you put 2 hydrogen and 2 water. 2 times 2 is 4. 2 times 2 is 4. 2 oxygen atom, because this 2 is for H and for O. Now, this is what we call stoichiometric equation. We need to make sure that this is correct. Otherwise, your material balance will be wrong. We are not chemists. We are chemical engineers. So most likely when your instructor gives you something in the exam, he or she will more likely to give you the already balanced chemical equation, just in case you know how to balance a chemical equation. Another thing that will destroy the material balance analysis, even if you reach to the stoichiometric equation correctly, is the fact that you choose a certain reactant and you find the fractional conversion of it, and it was not what we call the limiting reactant. We need to understand what we mean by limiting reactant. We have 50 mole H2 and 50 mole O2, and we wanted to find the fractional conversion to find out what will be the mole of water leaving. Will you start with hydrogen or will you start with oxygen? How to make sure that your reactant is limiting is by two methods. One is to find the stoichiometric amount of O2. You use the 50 mole of H2, convert it to how many number of moles of oxygen. To do that, you have the stoichiometric equation, and you know that for every 2 mole of H2, you have 1 mole of O2. 25 mole O2 tells us that we only need 25 mole of O2 if we have 50 mole of H2. But we have the real amount, which is 50 mole of O2, is higher than the stoichiometric amount of O2. It means we have excess. It means we have more than we wanted. And this will not be the limiting reactant. Now try to find the stoichiometric amount of H2. You do that by taking the 50 mole O2 and then you convert using the stoichiometric equation. You see the importance of the stoichiometric equation. It has to be right. The selection of the limiting reactant will depend on the stoichiometric equation. 1 mole of O2 is 2 mole of H2. This will cancel O2 with O2, and then you will end up having 100 mole of H2, higher than what we have, which is 50 mole. This is the real one. This is the supposed one that we need if we have 50 mole to convert to water, which means we will have shortage. The reaction will be run until we have 50 mole, but this 50 mole will go, and then still we have another 50 to reach 100, but we don't have it. This will limit the process, because what we need to have the ideal amount of water is 100 mole of H2, but we only have 50 mole. I know it is blah blah blah, but here is the other method that will make your life much easier. Divide hydrogen by oxygen, or divide oxygen by hydrogen, it doesn't matter. We will try this one. 2 hydrogen 2 divided by 1 O2. This is the stoichiometric ratio. Take the feed ratio, 50 H2 divided by 50 O2, which will be 1. If the feed ratio is less than the stoichiometric ratio, then it means what we put on the top is the limiting reactant, which means the one on the top, which is hydrogen, will be the limiting reactant. You could either do the logical solution, which I really like, but as a student I didn't like it, I didn't even understand it, or you use this one that will make your life easier. If the feed ratio is less than the stoichiometric ratio, then the one on the top will be the limiting reactant. Short story. Especially in the exam, you will be in a rush. You are not more likely to solve using the logic more than to solve using the algorithm itself. And come on, let's not fool ourselves. We are still, or were, students before, so we know the tricky things. And we will not take the examples that are easy, like water, hydrogen, oxygen, water. Let's take a real one. Call this A, B, C. 12%, and we have the shocking thing, 78% of air. You could choose a basis, like 100 bases, and then you multiply the 100 by each one of them to find the mole amount of each one of them. Start with B. I will put that in the denominator, which will be 12 mole, to find the feed ratio, divided by, let's take A for example, it will be 10. It has to be smaller than the stoichiometric ratio. If you take B divided by A, it will be 1. 12 over 10, it's not smaller than 1 over 1, B, not the limiting reactant. You don't have to find now the feed ratio of B to O2, because once this condition is not satisfied, it's not true, you skip B. Try, for example, A. 10 mole of A, and then I will divide it by NH3. NH3 is B. Maybe I forgot to mention that, but this is already balanced stoichiometric equation. You will notice that this condition is true, but that doesn't mean that A is the limiting reactant, because we still did not compare the feed ratio of A to C, A over C, but we don't have the mole of O2. And if you want to find it, you have 78 mole of air. And you should know, my friend, that 1 mole of air is equivalent to 21% of O2, or 0.21 of O2. It's the same exactly. If you cancel this with this, you will end up having 16.4 mole of O2. Put that in the denominator, has to be smaller than 1 over 3 over 2. It will be 2 over 3. This condition is actually true because this is approximately 0.6, while this one is 0.67. We made sure here that B is not the limiting reactant. Then A is the limiting reactant, which means if you find the conversion of the A, which is the propylene, C3H6, then you might be able to find the product leaving, which is C3H3N and H2O, and this will not make your material balance analysis wrong, because you did the stoichiometric equation and you found the right limiting reactant. To work on the problem the smart way, when you want to find out which one is the limiting reactant, basis is not important. Mole fraction will do, will be enough. What if we have 2 or more reactions? If you have A, it will produce B, and you have A, it will produce C. And you are told that the conversion, the fractional conversion, single pass or overall, I don't care, is 80%. Then 80% of what? Is 80% of A consumed to make B, which is what we want, or 80% of A consumed to make C, which is what we don't want? It's confusing. Conversion will not help you when you have 2 or more reactions. What you will count instead is what we call selectivity, and his friend or her friend, which is yield. We have 2 types of selectivity and yield, which is the instantaneous and overall. Instantaneous, you are more likely to use it whenever you want to design a reactor. You would need the kinetics of the reactor and the type of the reactor itself. Let's go back to the example and figure out how to find the selectivity and yield, overall kind of course. Say we have a chemical C, which is 20 mole going inside the reactor and leaves 75 mole C. If you want to find the selectivity, then simply you will say the desired divided by the undesired. The desired is what we want, which is in this case B. What we don't want is the C, 130 divided by 75. And the more the selectivity, the better the efficiency of the reactor. Calculate it, you will find it will be 1.73. If you want to find the yield, then the formula will be the real flow of the product divided by the ideal flow of the product. The ideal flow of the product will be if this 200 is completely consumed. In other words, what will be the flow when we have 100% fractional conversion of A? The ideal B that will leave will be 30 plus 200, and so the ideal of B, let's take it here, 130 divided by the ideal flow of B, which is 230, which will be 56.5%. The fractional conversion, the selectivity, and the yield will be types of information that we will need in order to completely solve material balance analysis for the reactive system. In the next video we will talk about something we really need also to find the flow that will leave the reactor, which is the extent of reaction.